Hello everyone, thank you for listening to this presentation. I'm Haoran from a California-based startup called Covariant. The company was founded by Professor Peter Bill and his students. Our mission is to solve real-world logistics problems with trustworthy AI robotics. If you're interested in more details, please come to the 5th Robot Learning Workshop, in which I will cover more details and answer questions. You've probably heard of a lot of progresses in AI, from deep learning to deep reinforcement learning to various applications to robotics. However, if we step out of the academic zone, what are the real challenges in the real world, in an industrial setting, and how do we build a trustworthy AI on top of it? Let's first consider traditional robotic automation. For this category of robots that are actually deployed and operating in the world, we see a highly structured environment where pre-programmed and deterministic behaviors do actually get the job done. For example, the robot is instructed to move from point A to point B and repeat the process forever. Once an engineer designs the environment and workflow, the same process can be automated because nothing is unexpected. While this has provided an incredible value for a ton of industries, from car manufacturing to chip design, there is an enormous market segment that cannot be served by traditional methods. However, if you look at some of the real logistics problems, the same pre-programming approach cannot work. The environments are less structured, there's a higher amount of variation, so the robot has to be able to perceive the environment, plan its actions, and react to online and changing situations. Coincidentally, these are also the types of tasks that we would like to automate because of labor shortage, worker injuries, and other issues. And that's what we do at Covariant. Here's an example application called Putwall, where our robot picks up random apparel items from random locations and placing them into designated positions so that they can be shipped to customers. Not only does the robot has to perceive and reason about the environment, it also has to adjust its online behavior so that it can transfer the object safely, stably, and also fast. Here's another application where our robot not only has to pick up random objects, but it also has to arrange them in such a way to maximally utilize the space available in the target container. Let's take a closer look at the material handling challenges that you might not expect in the academia. Some items are reflective, tightly packed, having repeated patterns, or just ambiguously overlapping in such a way that segmentation and depth reasoning is very hard. There are also literal corner cases, meaning that it's hard to grasp an object without running into collisions. Some scenes are so chaotic that you don't know which one to grasp in the first place. There are also dynamic effects. In this case, the box being transported actually has another object inside, and it falls out because our robot is moving too fast. Another difference from the academic world is that in order to deploy the robot, it has to achieve human-level autonomy so that the economics can be justified. While publishing a paper, it might be fine to achieve over 90% accuracy, but that means 10% of the time it will fail, which could be that a human operator has to stand by to catch the failures and fix it. Versus if the robot can achieve over 99% autonomy, that could mean that one operator can manage a whole fleet of robots that will deliver actual value to our customers. So how does Covariant handle all these challenges? Over these last 4 years, we have found 3 main pillars to focus on in order to achieve autonomy in a scalable way. As we will see throughout this presentation, scalability is a critical concept. If each AI robotics application required a large amount of targeted R&D work, the business case evaporates. The 3 pillars are composability, self or semi-supervised learning, and simulation. Let's dive in. The first pillar is composability. Let's compare composability with the main vein of recent AI and machine learning literature, which has a focus on end-to-end model-free learning. In other words, the system designer should just play an ultra-minimalist role. There are just system inputs and outputs with one monolith machine learning model in between. The end-to-end model has a unique strength. Because no a little structure is enforced on the model, there's no bias on it as well. In theory, it can achieve the optimal behavior. And that's what we have seen already for deep reinforcement learning agents to surpass humans on Atari games and even StarCraft. However, in an industrial application setting, the limitations of it, I believe, outweigh the benefits. First of all, end-to-end models are brittle to any modification. That is, if you specify a new task, typical architectures will not generalize elegantly. Often, you will have to retrain from scratch or even redesign the model. End-to-end models, by definition, lack interpretability. If you have some model failure, you can't do introspection to figure out why it happened. It also reduces trust from our customers because we can't explain what happened. In addition, the real world often has out-of-distribution scenarios that you cannot anticipate in training, such as the item in a box example I just showed you in the video. Model-free approaches tend to struggle more than other paradigms in such a context. Finally, in the reinforcement learning paradigm, you often need heavy reward shaping in order to achieve complex behaviors. At a certain point, the complexity of the reward becomes untenable. Therefore, from our experience, it is hard to make the end-to-end model work in the real world. At Coherent, we have taken the approach towards solving AI robotic automation by creating a platform on which we can develop high-quality skills that can be composed together to create a new system. In an analogy, a human has the ability to read, to perceive depth, to recognize objects, and to predict behavior of the environments. In the context of AI, you have several advantages in this approach. First of all, you can utilize the more dense supervision to train individual models. Compared to end-to-end training where there's only one sparse reward signal at the end, the object detection module can be trained through a massive amount of human annotations or even leverage existing models or public datasets. The composition of skills, instead of having a black box, also means that the robot generalizes better to real-world variations. There's another advantage of composability, which means that researchers are less likely to step on each other's toes because there is a clear boundary between what they work on. Finally, the composition of skills makes it easier to develop new applications. Compared to end-to-end, you don't have to change the reward function and or retrain the agent from scratch. Let's take object detection for example. You can't realistically expect an end-to-end trained model to be able to detect objects as well as a dedicated object detection model. But we realized that the current public state-of-the-art was not good enough for us. Most object detection work happens in relatively sparse scenes with minimal occlusions and overlaps. The examples are MS COCO, pedestrian datasets, and autonomous vehicle datasets. As you see from the examples above, we often are faced with incredibly clustered scenes of hundreds of items. Looking at the model prediction, notice the following things. First, the model is able to perform very well and output high-quality object masks. I sometimes even find it outperforming my own predictions. Secondly, the object can predict not only the visible part of the object, but also imagines the invisible part of it as well. And that's because for robotic picking, we need to know which part of the object is beneath another one. If we pick up the object on top first, there's a higher chance that we can put more suction cups onto the object below. And more suction cups means a more stable grasp. That's why we need to predict the invisible part as well. Let me further illustrate the benefit of composability. In robotic picking, we only want to pick up one object at a time, and that can already be achieved with the object detection model that I just showed you. However, sometimes it is inevitable to pick up more than one. In this example, two items are stuck together. So what do? We run the same segmentation model and find out that two items are being picked. So we put these items into an exception bin, and that can be handled by a human operator. The same error can happen when we're placing the objects. We run the same segmentation models and find out that more than one object is present. So we revert the conveyor belt and then return the object back to the picking toad. So in addition to having the object recognition model or skill being deployed to the typical pick and place application, we now have another application which is doubles detection. And that's one of the benefits of composability. Let's take a look at another example, 3D understanding. Almost all robotic applications need to have some kind of 3D understanding of the world around them, such as being able to avoid obstacles. When starting the company, we thought that the problem would have been solved by traditional industrial depth sensors. So we bought and evaluated the best sensors across all common modalities, such as LiDAR, active stereo, and structural light. Despite being almost prohibitively expensive, these sensors failed spectacularly on a variety of transparent and translucent objects. Here's an example of just a simple water bottle. Let's see how the traditional sensor does on it. You can see that the point cloud created does not even match the surface of the water bottle. So we had to use a learning-based approach and basically push past the public state of the art in terms of accuracy. Here's what our model can predict. Similar to how object detection model can be used for a different application, the same can be said about 3D understanding. Here's one example where the 3D understanding model gives the point cloud of the object, and we train another model on top to predict the 3D dimensions of it. Why is it important? Well, some customers like Lighthouse require knowing the exact sizes of the items that they are sending through a conveyor belt. We can send the same camera system to them and use the same 3D understanding model, but just train a small 3D dimensioning system on top of it. And the same 3D understanding model can be used for another different application. Here's an example that our customer wants us to place the objects very densely into the target container. So we simply pick up the objects, use the same point cloud and depth sensing model, and then train another model on top to predict the best placement locations in order to achieve maximal density. If you look at the diagram, then it's simply adding a head on top of the 3D object geometry model, and that becomes a packing application. So I've covered how covariance uses a composition of skills in order to achieve better performance and generalizations. Let's next take a look at the pillar 2, which is self or semi-supervised learning. So I've covered how covariant obtains different robotic skills such as 3D recognition and object understanding by training supervised models. But those have been very typical computer vision tasks. How does covariant actually assemble those skills into a very concrete pick-and-place applications by generating grasp points and trajectories? So that comes to the key part of our technology. Let's begin with grasp point generation. You might be thinking that this is as simple as, say, object classification, where you can have a human annotator tell where the robot should grasp. But if you do the math, you will realize something. If you have one robot station doing 1000 picks per hour, each pick requires 6 camera captures because we need to have 6 cameras to recognize the depth. If the robot runs 16 hours per day, 300 days per year, that equals 28 million images per year. If we have hundreds of stations, then we have billions of images per year, it will be impractical to get human labels on all of them. One idea could be that you simply prioritize human labels on the most important images. But how do we even know? On the other hand, can we just let the robot learn from those images without even having human annotations in the first place? It turns out that it's actually quite easy to know whether a grasp succeeds or not. In the case of suction cups, we can use high-quality gauge sensors to know whether the suction cup has sealed or not. In addition to the scaling benefit, we also find that this way of obtaining the ground truth is actually more accurate than human annotations. Here's one example where we turn on 2 of the green cups and disable 3 of the yellow cups. You might think that both the green cups can succeed in establishing a suction seal, but the left one actually doesn't, because there's a hole in the object and it's very hard to tell the hole if you just look at the images. And this is why knowing the ground truth data can actually help us a lot. So after the robot picks up the object, it needs to transport the object to the target location. In this process, the object might drop onto the ground because there isn't enough suction force available to support it. This is a very common issue and it has a very drastic performance impact. It also requires a human recovery, which might hurt the business case. You might be thinking that, simply slow the robot down. However, that will also hurt the business case because it cannot place as many objects as possible within 1 hour. There are some existing literature on the suction stability model, but they all assume rigid objects and rigid cups. And as you can see on the left, some objects such as polybags of apparel items are not quite rigid, and some cups can deform as well. And our solution is to train a suction loss model which, given the trajectory of the robot and information of the object, output the probability of the object dropped during transport. And luckily, we can use the same gauge sensors to obtain ground truth labels that we can train on, and we can use a vast amount of them because there are many robots running. In this case, the model predicts that at speed 1000, there's a high chance of dropping the item, but at 800, there's a much less chance. So the solution is to take speed 800, and then we can achieve both a high speed of transport and also a small chance of dropping the object. I just described how to train a suction loss model with just perception inputs. However, the weight of an object, which has a large role in determining suction loss, cannot be predicted from images directly. So what do we do? Well, we install additional sensors called load cells and IMU, which can detect forces, angular velocities, accelerations on the objects, and then we can use such sensor inputs and perception inputs to train a model that predict the weight of the object. So in some cases, we are able to acquire the ground truth weight of the object through the warehouse management system that our customers provide. So we can automatically acquire a large amount of training labels just through this process, and then apply the learned model to cases where we don't have the ground truth. The predictions of the model, which is the up weight, will be updated online dynamically, and the feedback controller will use the updated weight to automatically adjust the speed to prevent dropping the object. To summarize, in order to grasp and transport the object successfully, we need a suction seal model to inform the grasp sampling policy, a suction loss model, and a weight estimation model to inform the trajectory optimization process. Luckily, the ground truth labels of such models can be acquired from off-the-shelf sensors automatically at scale. And that's a very key part of covariance technology. So I just covered the other 2 pillars, composability and self or semi-supervised learning of covariance tech. Let's take a look at simulation. Simulation can be a very tempting way to acquire a large amount of data without too much costs. However, the seam to real gap cannot be underestimated. Models which perform well in simulation might perform really poorly in the real life. Here's a very simplified example where the training and testing distributions are very different, which explains why the robot could fail. However, sometimes it is necessary to learn from the simulation instead of from the real world. Learning through experience might not be an option all the time, because mistakes can be expensive or dangerous. For example, if the robot runs into a collision, it takes tremendous effort to repair it and to reset it to the original state. Sometimes, for robotic skills that we want to learn, the real-world data is either very expensive or noisy, and I will show you one example later. Let's consider 3D reconstruction. In this domain, real-world datasets are incredibly expensive to collect. A quick survey of the literature shows you that they are often limited to less than 100 examples. Consider the image below, which represents the workflow for collecting examples from the Middlebury dataset. The camera and lighting setup mimics the complexity of a movie set. Further, the item distribution is limited to whatever your data sensor can handle. In the Middlebury example, they have to first capture an image with their RGB sensors, then spray the motorcycle with a product that makes the surface more Lambertian, and then capture with the depth sensor. It should be clear that such an approach is neither scalable or practical for many use cases, including ours. Despite simulations being very critical for 3D reconstruction, such datasets, even are plentiful, are highly unrealistic and are wildly out of distribution for AI robotics. Consider the Flying Things 3D and Blended MVS datasets. They are nowhere similar to the pick-and-place applications that we run into in logistics settings. So to properly train a 3D reconstruction model that works well with the real world, we have found that it is necessary to generate our own simulated datasets that surpasses the state-of-the-art. In particular, it's better in rendering quality, object diversity, and scene and camera layout diversity. But a picture is worth 1,000 words, so let's play a little game. For the next couple slides, there will be 5 images from either simulation or from a real camera at one of our deployment facilities. Try your best to guess which one is real and which one is not. Okay, here's example 1. You have 10 seconds to tell whether it's real or not. 2. Example 3. Example 4. Here's the last example. Surprise! They are all simulated. If you've got it all right, congratulations! As I hope is clear from the examples, we have pushed hard to get the photorealistic datasets, and we have found that investments in such a direction is very critical in bridging the sim-to-real gap in our 3D reconstruction models. I would even say that the quality of such datasets is more important than whether your model has all the latest bells and whistles and model architectures. We are by no means done when it comes to simulation. Some important next steps include automating object mesh and texture, which is by far the most expensive part. One idea is to have a workflow where the bot tender can collect many camera captures of the object in various poses. Using this data, we can generate photorealistic 3D meshes and the associated textures. then this will help us scale our already large dataset by many orders of magnitude. Finally, we want to pair this impressive rendering capability with equally good physics, and that can correctly model object-to-object and robot-to-object interactions. With that, we can train and test even more of our stack in simulation. To summarize, we've discussed the state of the art in AI robotics and the three most important pillars to trustworthy AI robotics. Composability, meaning that models can be developed, debugged, and reasoned about independently. Self and semi-supervised learning, meaning that we can acquire a large scale of real data to improve model accuracy. Simulation, meaning that we can acquire a large amount of data that is impossible or expensive to get from the real world. Before I close, it's important to recognize that the work here I presented today is thanks to the entire team here at Covariant. If you are curious to learn more and help us in our mission to enable the next generation of AI robotics, consider sending us an email. Thank you.